Okay, so yesterday we spent the whole day talking about the impact of random assignment within where this random assignment is replicated across a bunch of sites in a multi-site trial. And today we're still going to talk about multi-site trials, but we're going to confront the reality that in a lot of cases, people don't do what they're assigned to do. That is, in fact, that happened yesterday when we gave you an assignment, and I'm sure you did it, probably because we confused you and we misled you. But so people are assigned at random to a treatment, but people who are assigned to the treatment may not participate in the treatment. And in some cases, people who are assigned to the control group may end up showing up in the treatment. And so how do we estimate the impact of program participation? That's going to be the focus of this morning. And it's going to be actually a very simple case of a mediator. Because although if you read that, we're going to use instrumental variables. If you read the literature on instrumental variables, they don't necessarily use the word mediation. I don't usually see that word. But it really is, because you're saying, well, by what mechanism does being assigned to the treatment affect your outcome? And sort of just, very simply, well, by participating, right? If you don't, and so the general assumption, one of the big assumptions is in this instrumental variable world is going to be that the only way that assignment to the treatment can affect the outcome is if you participate. And so that's going to simplify, it's going to tremendously simplify the triangle, because it's going to wipe out the other pathways that go from treatment to the outcome that don't work through participation, right? So we're going to start with that and try to really understand that, try to understand the assumptions behind that. And it's another case where the world is going to be really pretty simple if we're willing to assume a constant treatment effect. If the impact of assignment on participating is the same for everybody, and the impact of participating is the same for everybody, you're going to see that it's really straightforward. And we're going to look at that case first, just within one site. So we'll start with a constant treatment effect in one site, and then we'll say, but wait a minute. This, although people have been doing this for many decades, blissfully, it might not be very realistic to assume homogeneity of impact of those two kinds of impact. So we're going to introduce the idea of heterogeneity. Then we're going to see what happens and how things get a little more complicated. Mainly, we're going to see that we have to impose some other assumptions. If people are responding heterogeneously, that's really going to require us to think hard about assumptions. Kind of the same thing we did yesterday, homogeneity, if you're willing. That's a very strong assumption. If you make that one, you don't have to make too many more. But if you have heterogeneous impacts, then you have to think of some other assumptions. And so the idea would be, if we can master this very simple example of mediation, where you have this single mediator participation, then we can graduate into the world that Sean is going to talk about after lunch, which is where you have more than one mediator, and things get more complicated. But I did want to ask how many people in the room have ever studied instrumental variables. And okay, and I always noticed by the way people raise their hand that you really did study it. Okay, that's good, because you didn't just go like that. You went like that, So, and what about the idea of a local average treatment effect or a Complier average causal effect? Those are synonyms. Yeah. Okay. A lot of people. Okay. So, did anybody never study that? Is there anybody who hasn't studied that? Don't be shy. Okay. So that means I should go pretty fast through that. I'm gonna do that. No. Yeah, maybe not. Well, let me see how it goes. Because see, so really our project, that stuff has been known for a long time when you assume homogeneous treatment effects, and for at least, I don't know, maybe since, I guess, Angrist, Imbens, and Rubin, 1996, or right around that time, Angrist and Imbens, 94, the idea of heterogeneity. I guess Jim Heckman with his random coefficient model back in the 90s, or even maybe for him a little earlier, the idea of heterogeneity came in. But it was pretty much always, as far as we can tell, for one site. All of that stuff, that great classical stuff, is for a single site. So our project is to take that stuff, really understand it, and then say, what happens when we go to multiple sites? That's really what this is all about. Okay. So, so here's my outline. So we're talking. So this is this business of estimating the impact of participation. Obviously, if everybody does what they are told, then the impact of assignment is the same as the impact of participation. We can just study that. But the problem comes up under the label of non-compliance. People in the experimental group, assigned to the experimental group, don't do what they're supposed to do. They don't take up the treatment. People in the control group do, perhaps. And so it's, we're going to see that non-compliance is pretty pervasive in most of these big multi-site field trials. Just give a few examples. We'll talk about the instrumental variable in a single study. If the impacts are homogeneous, kind of the classical way people did it for many years. We'll introduce the idea of heterogeneity, give an example or two. And then we're going to move right to the instrumental variable in multi-site studies, and we're going to give you a few, a couple of ways of taking this to the multi-level case, where we're going to want to, again, just as yesterday, we're going to want to estimate the average impact across sites, but we're also going to want to characterize the heterogeneity. We really want to look at the heterogeneity of the effect, not of assignment, but rather of participation, and that's relatively newer stuff. We'll talk maybe a little bit about design and maybe conclude by thinking that, gee, these two things, getting people, if you're running a program, getting people to participate and making the participation count, making it have an effect, those are the tasks people who run programs. And what we'll see pretty quickly is that the overall effectiveness in the sense that the effect of being assigned to the program is going to be the product of those two things. And we're going to talk about maybe modeling, just in general, a little bit about modeling those two things, understanding those two things, and why that's of practical use. So, so we talked yesterday. I mentioned that IES, and this is from Jessica Spybrook's work, has funded a huge number of group randomized trials. And there's a lot of examples outside of education. Just talk a little bit about the problem of non-compliance and the fact that it's pretty pervasive. So in the National Head Start evaluation, which Howard and Mike both talked about, people were assigned to be in Head Start or not Head Start, and but there were different things you could actually do. You could, a person assigned to Head Start could do what they were assigned to do, which is to send their child to Head Start, right? Or they could decide to keep the child at home, or maybe some home daycare kind of arrangement. Or they could go to another center. And going to another center, this is really a problem because a lot of our theory would say that a lot of these other centers should probably be about as effective as Head Start, that really what you want is have your kid in center care, that, you know, that works pretty well. I mean, a lot of people would say that. So that makes it a lot more complicated. And so the people assigned to the program, I guess, what was it, about 75% who actually, of those assigned to Head Start, went to Head Start? Oh, about 85. Okay, so. Oh, okay, about 85% of the people who, okay, that's good. About 85% of the people who were assigned to Head Start actually sent their child to Head Start. But then, I guess another, what, 10% or so of this control group got somehow, their kids showed up in Head Start, right? Right, so 85 and 10. So then the impact of being assigned, right, is going to increase the probability of going to Head Start by, on average, 75%, 85. Because 85 probability is 0.85 if you're assigned to Head Start, 0.10 if you're assigned to control. The difference, the impact is the difference in those two probabilities, 75%. So we could call it sort of 75% compliance, right? Okay, so that's the idea. Let's see, what else? Moving to opportunity. How many people have heard of the Moving to Opportunity study? This is a little bit away from education, but a lot of you know about it. This is where, in 5 cities, residents of low-income housing projects, living in very low-income people living in typically areas that have concentrated disadvantage in these housing projects, are being randomly assigned to get a voucher. And probably the most interesting aspect of the study was that that some people were randomly assigned to get a voucher where they would be moving to a low-poverty area. So that was what the voucher was for. And so there was a group of people who didn't get that. Well, it turned out that only about 47% of the people used the voucher. So, and there's a lot of reasons for that. I mean, for one thing, in some cities, particularly cities with tight housing markets, landlords don't really want people with Section 8 vouchers. And, they don't. Some of them, they'd rather take people who can pay for it on their own. Maybe they have some bias against people, and since the housing market is so good, they can just deny people who have a voucher. So it's pretty hard to lease up in some of these environments. But 47%, even though the voucher is worth a huge amount of money, like something $8,000 or $10,000, it's worth a lot of money. So so in the experimental group, people assigned to the experimental group, 47% comply, or do what they're supposed to do, 53% don't. But in this case, it's a little different from Head Start. No one in the control group got a voucher to go to a low-income area. So I think some of you in our discussions call this sort of one-sided non-compliance. There's only one way you can not comply, and that if you're assigned to get the voucher, you can decide not to use it. But if you're in the control group, you'll never get the voucher. So there's nobody who's ever going to show up getting the voucher. And that situation is a little simpler, actually, where we can do more in that situation than when both kinds of non-compliance occur, as happened in Head Start. In most of these school-based lottery studies, I see 0.50 as being kind of a pretty typical number as the fraction of people who comply, because like I've done one of these in Chicago with just with 2 elementary schools that we wrote a book about. About 75% of the people who were assigned to who won the lottery were immediately offered a seat. Of those immediately offered a seat, about 75% of them took it up. They said, okay, I'm going to go. And then of the control group, because they're put on a wait list, 25% of them showed up, right? So 75 minus 20, 50% compliance. So you can look at these studies and you see this, you see it's pretty pervasive. I guess it didn't happen in welfare to work. Yeah, because everybody in welfare to work was subjected to these rules. If you don't follow these rules, you're going to be kicked off of welfare. Is that right? Someone want to say something about that? And nobody in the control group. They were getting the then conventional form of welfare, which was AFDC, Aid for Families with Dependent Children. That was by law. That's what they were getting. The other ones who were going to get this, and they really didn't have any choice. So they were all subjected to the same rules. So there's there's all. Right. Yeah. So okay. So we don't have to keep belaboring. I think you get the point. I mean, but non-compliance is fairly pervasive, and there are exceptions. But you're out there in the real world. It's not a laboratory experiment, where you're controlling everything, and people are making decisions, and stuff is happening. Other people, like not only the people who you assign, but in the case, it's not just that the participants are freely making choices. I mean, in the case of moving to opportunity, other people like landlords are constraining what you can do. So the world isn't letting you do the experiment you really want to do. So stuff's happening, but we really want to know. I mean, typically, we really do want to know what is the impact of actually participating. What's the effect of actually moving to a low poverty area? I mean, that's kind of the issue, right? I mean, most people who thought about this might not think that. What's the effect of being assigned a voucher? Although. Actually, the Housing Authority probably cares a lot about that. They want to know if we assign so many vouchers, they want to know what's the effect, but they also want to know how many people are going to take it up, because if they thought that it was going to be 47% and everybody took it up, they'd quickly run out of money. I mean, they'd be giving out more vouchers than they can support. So a lot of times policymakers actually do deeply care about the intention to treat effect, what we talked about, even if there is non-compliance. So it's good to think. In fact, you have a little assignment where we're going to ask you to interpret these effects. Talk to somebody. Tell somebody what are you learning. We're going to give you some results from that Howard and Mike came up with out of the Head Start study, and say, here are these results. Tell somebody what this means. Okay, and so you have to put some words around this, and tell people what your assumptions are. We got to get into that. Okay, so so we've kind of done that. All right, so let's assume now that we have homogeneous treatment effects. Then, you've probably seen some, I don't know if people still teach, do people still teach path analysis? Does that come up? Or causal graphs or something like this, where you see I guess that, that was really big, I don't know what, 10 years ago? I guess it's out now. People don't do it. But the idea is that, and we could maybe use, Head Start as an example. So T is going to be random assignment. So T is going to be a 1 if you're assigned to Head Start, and a 0 if you're assigned to the control group, right? And so what's the effect? And so we're going to, so we want to know what's the overall effect of T on Y, ignoring participation. That's going to be the intention to treat effect, right? What's the effect of random assignment on the outcome Y? That's our intention to treat effect. But what we're going to say is, well, it works through whether or not you participate. The effect of being assigned is, if you're assigned and you participate, it makes you participate, then participation is going to make you have this effect, and it's going to work. That's going to be the mechanism, right? And the assumption, the key assumption is going to be that if you don't participate, T isn't going to have any effect, unless you think there's something. I mean, you can think about it. Maybe if you got the news that you won the lottery, it just changed your life. Your self-esteem went up. You got really excited. You got really happy. I won the lottery. Did you ever see The Jerk by Steve Martin? Remember when his name was in the phone book? My name is in the phone book. He was so excited. It really made his day. So, so usually we kind of think that's that's not going to really happen. Just being assigned isn't going to, especially the Ys that we're talking about, things like how much education you get, how much money you earn. I mean, you might be excited for a couple of days about the fact that you actually won the lottery, and you must be really wonderful, because when you win a random lottery, it really shows how good you are. But that's not going to make you earn more money, get more education or earn more money. Something more profound has to happen. So we're usually going to assume that T doesn't affect Y unless you participate, okay? That's called an exclusion restriction, because in a standard path analysis, there would be an arrow going here, and we have erased that arrow. So we've excluded that pathway. So that's called an exclusion restriction. Very strong assumption, but in some cases, in this case, it's probably not that strong, because it's pretty plausible. It's not going to. It isn't going to happen. T isn't going to affect Y except through M. So if we think that gamma is the average, or not the average, if gamma is the impact of T on M, and if T and M are both binary, right? T is a 1 or 0, and you participate. That M is a 1 or 0 also. All right. M is a 1 if you participate, a 0 if not. So gamma is really a difference between two probabilities. It's the effect of T on M is the difference between the probability of participating if you're assigned versus the probability of participating if you're assigned the control. So that's gamma. And the effect of participation, so maybe somebody can help me. Delta, if this is binary, M, Y, what's delta? What kind of a scale is that? What kind of a thing is that? It's a parameter. What is it? If Y is, okay, well, sorry, I should have told you. Y, let's assume Y is a continuous variable. So something like the Peabody picture vocabulary test, which we treat at least as being a continuous variable, or something like that. So delta would be what? Would it be a difference between two probabilities? Just to think about what it is. Anybody? I guess you all know the answer, right? You know the answer? Right. It would be, yes, it would be. And actually, that's a good way to say it, because we're assuming homogeneity. So when you say the difference between your outcome if you participate and your outcome, because it's the same for everybody. It's also the mean difference, right? So, it's like a difference between two means, the means of people who do and don't participate. Okay, so now, in these path diagrams, a lot of times what people do is they do a regression where the outcome Y is going to be regressed on T and M, and that's kind of a natural way to think about it. Let's just take the outcome, which is your vocabulary, Peabody picture vocabulary test, and you're going to regress that on, use that as a predictor, M. In fact, here you really don't, if you want to know what the effect of, if you want to know what delta is, you could say, well, I don't even have to, there's no path, there's no direct path. I don't have to include T in the analysis. I'm just going to regress Y on M. And it's pretty straightforward. Any problems with that? Anybody? This turns out to be kind of not what we want to do, necessarily. I mean, it's easy to do. Just take Y, go to your favorite package, do a linear regression. Y is predicted by M. You get a mean difference between two groups on M, but yet we're going to do something. Why don't we just do that? It's so easy. We're going to do something that's going to be more complicated instead. Why are we just trying to make life difficult? Anybody? You want to say why? Why? You don't know why? Any problems at all with it? Okay, so what are you saying about random assignment in this case? But if I have M and I already know what it is and I know whether you participate and I know why can't I just do a regression of Y? Yeah, forget about T, just ignore it. Who cares? There's no path between T and anything wrong with that? No, go ahead. Go ahead. You're, Right, but why do we care about that? I mean, that's what I'm trying to get at. Why do we really care about the first stage? You know, suppose I just gave you a data set and I said, here's a bunch of M's and here's a bunch of Y's, and I didn't even tell you about T, and all I know is did people participate in this? Ooh, somebody over here. Okay, so M is not randomized. So M is you know, like in right. I mean, that's where you're going. In the moving to opportunity, whether you participate might be determined by, you know, the landlords you happen to encounter and, you know, which neighborhood you were looking in and whether they like Section 8 people and stuff like that, or other stuff about, you know, whether you had your stuff together well enough to actually go and find out where the units were and visit the units and all that kind of stuff. So M was not randomly assigned. So the regression, the mean difference between just the observed mean difference in our sample on Y between those who did and didn't participate could be very badly biased. There might be some people who are really gung-ho and they're going to do everything under the sun to participate, looking at 27 houses, and, you know, even though 25 landlords said they wouldn't take you, they found those two, you know, and other people after 5 landlords said no, they gave up. All right, so there's this selection bias, and so you might have the people who participate might be the ones who are going to have the best outcomes anyway, right? You know, or another thing, it could be that the people who are going to participate are the ones who really know that they have such a bad housing project that they know it can't get worse. I want to go somewhere else. Other people have a housing project. They're pretty happy. It's pretty safe around there. They have a lot of friends and family members. Maybe it's going to be worse out there, so maybe they don't participate. So you see what I'm saying? The people who know they're going to benefit from the treatment might be the ones who are going to participate if they know that. You know, so you know, there's kind of two kinds of bias, right? But anyway, so we're not going to do that. Now, we have constant treatment effect. We don't have to worry about that. We just have to worry about the fact that that some people are going to benefit more than others because everybody benefits the same. But the people who are going to participate might be the people who would have done well anyway. All right? So what we're going to do is we're going to exploit randomization twice. So in a path analysis, just you know, in a path analysis, the total effect of Y of T on Y is the product of the indirect effect plus the direct effect. That's why I said it works nice if you know path analysis. That if you want to know the effect of T on Y, it's gamma times delta plus this pathway here, which we've excluded. So that means beta is just equal to gamma times delta plus another direct effect that's assumed to be 0. So that means we can just simply do the division. We can do the beta divided by gamma thing. And the beauty there is that beta is the intention to treat effect of T on Y. And gamma is the intention to treat effect of T on M. So both beta and gamma are protected by randomization. So they're both unbiased. And by estimating those two things and by excluding that direct effect, then we can just do this division, assuming gamma is not equal to 0. I mean, if gamma is not equal to 0, that means that the effect of random assignment has no effect whatsoever on participation. You're never going to get anywhere, and the math kind of telling you that because you're trying to divide by 0 here. It's not going to work, right? So there has to be an effect of T on M. Okay. So this is a really cool trick. We exploit randomization to get beta and gamma, and we divide those things to get the thing that we can't get directly just through doing a regression. Okay, is that clear? I guess you guys all know this stuff. All right, so let me move on. What happens when we have heterogeneity of impact? See, so we've assumed, so the assumption of a constant treatment effect, that's a woefully strong assumption. So we're going to abandon that. We're going to say people can respond differently. That when some people, so this is going to be a person-specific path diagram. I don't know if you've ever seen, how many people have ever seen a person-specific path diagram, a causal diagram? These are very useful, actually. They help you a lot. So T is for me. Did I get assigned at random? And gamma, this big gamma, is going to be my person-specific effect of T on M. And so I'm going to get a 1 or 0. I'm going to be assigned a treatment or control, and M is either going to be 1 or 0. And so the effect of T on M for me is going to be capital gamma. It's going to be a random variable that varies over people. That's going to have a mean in the population of little gamma, the thing that we just looked at. Okay? And then the same thing. Delta, capital delta, is going to be the effect for me of M on Y. So everybody has their own little personal effect of, everybody's different, and their circumstances are different, and therefore participating is going to have a different effect. It's going to depend on all kinds of stuff about me. It's going to depend on, like in the moving to opportunity, which neighborhood I happen to go to, or and so forth. In Head Start, it's going to have to do with, effective participating is going to have to do with not only how good my Head Start center is that I might participate in, but how good my alternative might have been, my counterfactual. So we got a lot of reason to think there's heterogeneity. So it's true that for any person I, BI, which is the intent to treat, Howard showed you, it's Y1 minus Y0 for that person, right? It's the causal effect for that person, which we can never compute because we'll never see Y1 and Y0. We can't compute the intention to treat on every person, but in principle it exists. And what this path diagram says is that the intention to treat effect for me, I'm person I, is the product of my gamma times my delta. And then the key problem comes up when we take the average. Well, now we want to just, okay, no problem, we're just there, that's fine. Let's just take the average of those over the population. Unfortunately, we get this thing called, the product, the expected value of product of two random variables turns out to be the product of their means plus their covariance. Okay? Plus the covariance of gamma and delta. So it's really important to think about what this covariance of gamma and delta might be. Because see, now if we divide by, you see what happens if we divide by gamma, we get delta plus the covariance over gamma, which is this bias term. So we get this bias term. And what this is really saying is that you're going to get a really big effect of assignment if there's a really big effect of assignment on participation, and if there's a really big effect of participation on your outcome, and if the people who comply with assignment are those who are going to benefit the most. So this is where sort of the selection bias creeps back in, because maybe the people who know that they're going to benefit from Head Start are those who are going to comply. They're going to take up Head Start because they know, or maybe they don't know, but they are, in fact, going to benefit most. So an example would be, I'm a mother, I have a little kid, and the Head Start center near me, I think it's kind of okay. It's quite good, and I know that if I don't send my child to Head Start, I'm going to have to send my child to Aunt Susie, and Aunt Susie parks her children in front of the television all day and feeds them junk food. Okay, so I'm going to decide that if I'm assigned, I'm going to take it up. I'm going to definitely send my kid to Head Start, no question. Yes. Well, here's what I'm saying. So if what I'm saying exists, if scenarios like what I'm saying, kind of, I'm just exaggerating a little bit. So let's say that on the other hand, I'm a mother, and I'm trying to decide, if I'm assigned a Head Start, I'm going to send my kid. But I know, my aunt Susie has a PhD in child development and is the best teacher of language and reading and math that ever walked the face of the earth. I'm not going to send my child to Head Start because I know that counterfactual is a really good thing. Are you with me? You see what I'm saying? So if people are heterogeneous in terms of their of the quality of their Head Start centers and the quality of their counterfactual alternatives, then they're going to have different deltas. And if they know anything about that, if they have any foreknowledge of then they're going to have different gammas. So really, it's not hard to spin out a theory. I don't know, there's, Howard, any other theory? I mean, it's not hard to spin out a theory where gamma and delta would both be heterogeneous. Yeah. Okay, so that, it's kind of, once you start telling these stories, of course, you tell these extreme stories, you realize people don't have that. It's, Aunt Susie is a PhD versus a horrible caregiver. That's kind of extreme. But, if you sort of think about the variability in people's circumstances, or, some people live 3 miles from the nearest Head Start center, and it costs a lot of money to get there, and, they have a job, and they can't have to get up. It's hard to get the kid there and get some other person at Head Start centers right across the street. That could affect your gamma, right? I'm not saying that would affect your delta, but it would certainly affect your gamma.
I feel it's easier to think about human effects are heterogeneous than homogeneous.
It is. It's really hard to think about them being homogeneous. I'm not saying they can't be, but it's just kind of hard to just take that as like our starting assumption is everybody's going to have the same gamma, everybody's going to have the same delta, and as a result, everybody's going to have the same beta. That's just really, even though see, I think people read all this literature on experimental agriculture, and they had also all these things, and they sort of thought that, one soybean plant is like another, and one plot is like another. Oh, that probably isn't true. It's probably not really true. But there's probably less heterogeneity. Now we're talking about human populations living in diverse circumstances. It doesn't translate. Okay. So, so this piece is kind of tricky, and we got to keep this one in mind. This, we're going to try a couple of ways of trying to make this go away. If we can make this go away, then when we divide by gamma, we're going to get delta. If we can just kind of make this go away, right? And there's we have 2 strategies for making it go away. The simplest is, let's assume it's 0. That's kind of, let's assume we have a can opener. We got a can here, and we can't open it. Okay, so, we're just going to assume that, people vary in their gammas and people vary in their deltas, but they're not correlated. And that's weaker than assuming a constant treatment effect, but it's still maybe pretty strong because that, like, if people my delta is let's say Howard's delta is bigger than mine, and my gamma is bigger than his, or whatever, but we don't know anything about our deltas, so so they're just random, yeah. Right, okay.
They have to know these things, and they have to be right in order for these correlations to exist. So there's some room for slippage here in that code.
Right. But they don't, so it could be, there are other ways. So let me go back to housing voucher. So if, let's say that in cities where there's a very high rental market, if people would benefit more, or let's say from a housing voucher, and the gammas are smaller because the landlords don't want you to, they don't want to give you an apartment because you're a poor person, right? So, the correlation can be created with, through other mechanisms other than the foreknowledge. We usually think of the foreknowledge as having a big, but we don't want to pretend that people are, I'm in sociology, so I don't want to pretend like a lot of economists do that people just have a whole huge array of choices that they can make. We know they're constrained by reality. But the constraints could generate, the constraints people face in reality could also generate a correlation. So, and I agree with Howard, a lot of times when you analyze these things and you use the methods that assume homogeneity, you still get pretty reasonable results, even though but it's just, we don't want to start there, okay? Okay. So one strategy for just making the covariance go away is by assuming it's 0. There's another one that maybe that's a strong assumption, fairly strong, not as strong as a constant treatment effect, but it's somewhat strong. No covariance between gamma and delta, right? That's 0. We do the division, we're home. Another one is to go after, and you guys have studied this, the local average treatment effect. And this is your first introduction to principal stratification, because this is what Lindsay's going to use this. But here's a very simple case. We're going to say that you can subdivide the population into 4 groups of people. The population of mothers, let's say in Head Start, consists of 4 different kinds of people. The first are, and they're defined by their potential mediator values, so potential outcomes. We don't see these, we don't know who these groups are, at least not right away. We can kind of figure out to some extent who they are. We'll see it later. But the compliers are the people who would participate if they were assigned to Head Start. M1 is the value of M, participation, when the T is equal to 1. And so for the compliers, it's 1. That means if I'm a complier, if I'm assigned, I participate. And I'm such a nice person because I'm really trying to help you with your study, right? So if I'm assigned to the control group, I'm not going to participate. So that's called a complier. We like those people, right? They do what they're told. They do what the experimentals want them to do. And therefore, their gamma for those people is M1 minus M0 is 1. Right? But then there are these other kinds of people who are kind of irritating. The always takers are the people like in Head Start. These are the people who, if assigned to Head Start, they definitely are going to go. They're going to have their kid go to Head Start. So M1 is 1. On the other hand, if they're assigned to the control group, they're still going to send their kids to Head Start. Maybe this is the one who has the Aunt Susie, who's the horrible caregiver, the only alternative. And even if I'm assigned to the control group by hook or by crook, I'm going to get my kid into Head Start. I don't care what I have to do. So my M1 is 1, my M0 is 1, my gamma, therefore, the effect for me of assignment on participation is 0, right? And therefore, because of the exclusion restriction, I didn't say here, the compliers Y1, that's my value of Y if I'm participate versus Y0 is going to be my causal effect. But here, down here with the always takers, Y1 is the outcome that I'm going to get if I go to Head Start, and Y1 is the outcome I'm going to go Y1 is, if I go to Head Start. I'm going to go to Head Start either way. This is if I'm assigned to treatment, assigned to control. I'm going to still always go to Head Start. Under the exclusion restriction, the only thing that really matters for my outcome is did I participate. I'm going to participate either way, therefore the causal effect for me of assignment has to be 0. My ITT effect has to be 0 under the exclusion restriction. Are you with me? And then the never takers, these are people who, Aunt Susie is a PhD in child psychology, so if I'm assigned to Head Start, I'm going to send my kid to Aunt Susie. I'm not going to participate in Head Start. If I'm assigned to control, I'm still Aunt Susie, and I'm not going to participate in Head Start. Therefore, it's going to be Aunt Susie, so Y0 minus Y0 is 0. There's not going to be any effect of being assigned to the treatment, right? Okay? Yeah. Question? Yes? Yes. Thank you. Yes. Thank you for fix that. Yeah, that's right. Okay. Yeah, I don't have my own computer. Otherwise, I'd fix the slides right now. Okay. Thank you for that. So then there's this other group of people. Now, these people exist for the sole purpose of screwing up your study. That's their purpose in life. Because if they're assigned to Head Start, they're not going to participate. And if they're assigned to the control group, they are going to participate. So whatever they're assigned to do, they're going to just do the opposite. Why? Because they want you to have a bad study. So the effect of being assigned to Head Start on participation for them is -1. And therefore, they have this weird treatment effect. Okay, so the way we're going to get rid of the no covariance problem is we're going to assume those people don't exist. Right? That just is too hard to believe that there's somebody who would really prefer to go to Head Start, not to go to Head Start if they're assigned to it, but if they were assigned not to. They're just these very contrarian people. We're going to assume, or that the fraction of those people in the population is negligibly small. It's effectively 0. Yeah. Oh, The Simpsons, the cartoon, you mean? Yeah. 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 Bart is always going to do. Yeah, he's kind of a menace, right? That's right. So, so the fraction of the population. So gamma is the fraction of the population who are compliers. Gamma compliers. Gamma always are the fraction who are always takers. Gamma never are the fraction. And we're going to assume this is 0. And by assuming this is 0, and since only one of these treat groups is going to have an effect, and we'll wipe this group out, because see, this group could have this weird effect, but there aren't any of those people, so we don't. This isn't really 0. This could be something else, but these people don't exist, so we don't care about that. So that means that we can partition the expected ITT effect. The average is going to be, you know, this sum of effects times probabilities. It's going to be the effect delta compliers for those who are compliers times the probability of being a complier plus the effect of 0 for the always takers times the probability of being always a taker plus the effect 0 for the never takers times their probability. And the 0 times those things goes away, and therefore the average ITT effect is going to be delta gamma, where delta is actually the effect on the compliers and gamma is the fraction of people who are compliers. And from now on, gamma compliers, we're just going to call it gamma. Okay, just because I don't want to keep writing the compliers thing. And now, hey, I can do the division and get delta. But we got to remember that delta got redefined. It's not the average effect of participation in the population anymore. It's the impact of participation for those people who complied. Or you can say, one way to say this that's kind of nice is to say, for those people who were induced to participate by randomization, they were induced to participate. It's the effect for that group of people. So that's kind of a nice thing. So we have a causal effect now under a pretty weak assumption. The assumption that these guys don't exist is called the assumption of monotonicity, because what we're saying is that being assigned to the treatment cannot reduce the chance of participating. So monotonicity says being assigned can only have no effect or a positive effect. So that's why we use the fancy word monotonicity for that. So now we're not assuming a constant treatment effect. We're not assuming no covariance between compliance and effect. We're assuming monotonicity. But now we've got a delta that's a different delta. It's the causal effect for the subgroup of people who are compliers. And there's some problems with that come up, particularly in the double-sided case, because we really don't know who those people are. And we don't know. So when we get to multiple sites, one of the problems are going to be in one site, the compliers might be a different group than in another site. Like maybe in one site, people really, the program people did a really great job of getting people who would have to comply. They're just really good at getting people who are assigned to participate, and they want everybody. In another site, they're not good. In fact, if you don't look like a pretty cool person, they're just as happy if you don't participate. So their compliers are different. So the compliers in one site are different from the compliers in another. So this is kind of a problem that we're going to have to cope with. In combining in any study or in any site.
Ask you a question, Steve.
Sure.
So how is the fact that compliers are different across sites fundamentally different, or is it, than the fact that your samples, your populations are different across sites? They're fundamentally different.
I think you have not rid yourself of confounding. That's my own view, and the reason I say that is potentially, if you can make up stories. It's always good to make up stories, even just to think about it. So one story would be that if you're very fussy about who you encourage to comply, you might encourage the people who are going to have the best effect, and so the sites that have the lowest compliance might have the biggest effect. And they might look like.
All sites have the same effect for the full population, even though that's a possibility.
Right, they could all be subsets. People could be randomly assigned to sites. Right. And the site directors in one site. So here's an example. When I first got started in education before I went to graduate school, I worked with a program called Upward Bound. Everybody heard of Upward Bound? They take kids who are low disadvantaged kids and try to help them go to college. And there were sort of roughly speaking two kinds of Upward Bound programs. There were the ones that were kind of searching for the talented 10th, and then really encouraging those kids. They were sort of a talent search. Let's find the diamonds in the rough. And they're the ones who said, let's just take all the kids, the ones who are really disadvantaged, and see if we can really make a difference for them. So they had different, the managers of the program across the country had different orientations. And so, you could imagine having different effects. So I think that, and potentially, this may be an extreme to think that people are so heterogeneous, or sites are, or that people have these malevolent intents or different intents, but you really haven't totally solved the problem of confounding with the local average treatment effect. You say, you're avoiding this strong assumption of no covariance, but the covariance is still there. It's still there because if one compliance group is more rarefied than another, there could be, the covariance is still going to pop up and hit you. I don't know, what do you think?
That could exist across sites.
Yeah. But it also can exist in any one study. Pardon me?
You could have
Yeah.
a stronger population here, a
Right.
weaker population here, and so on and so forth. And you still, some sites are getting bigger effects for their clients and weaker effect, and they're starting out with different populations.
Yeah.
Here you're starting out with different complier populations.
Yeah.
It feels like the problem is similar. It feels like it's one of generalizability more so.
But usually, okay, so here would be my counter to that. If let's say you have perfect compliance, and we have ITT effect equals the effect of participation, and we have this in different sites, we know who those people are, and we can measure lots of things, and we can tell people who they are, and we can study these effects of, like, let's say one site is mostly of one ethnic group, SES, gender, whatever, and another site. We can kind of try to have some theory, and we can actually measure these things, and we have some observables, and we know, we can identify who the people are in the different sites. Whereas here, the problem is we have these latent groups, and we don't know who's in them.
But you can describe them in the very same way you
Yeah.
can describe the
Okay.
population, you can describe the
Okay.
complier set of populations.
All right.
I'm going to stop.
No, I'm with you. But there was another comment over here. You had a comment, right? Yeah. Yeah.
Like, could bias creep in if, let's say, one site runs the program better,
Right.
therefore induces more people to comply?
Right.
And so you still kind of have across site this correlation between compliance and effect.
Yes. Well, you still have it, and you're not assuming it's zero. You have it, and you're getting these local average treatment effects. You see what I'm saying? But you're trying to interpret them. You're trying to interpret them.
Local average treatment,
Yeah.
right? But then if you look at across sites, and there's still a correlation between the cross-site compliance and the cross-site effect, does that create bias? So, like,
No, it doesn't create bias. It's just that every site has its own subpopulation of compliers. We don't know who they are, and they have different effects. So, it just opens up some question. I'm agreeing with Howard. We can do a lot more to try to really probe that. We just have to realize that it's not a magic bullet. And I read a lot of things where people say, they estimate the local average treatment effect. They say that's the causal effect, and then they just go home. They don't, so yeah, I think we should be a little more careful. Yeah, comment over here. Yeah.
Yeah, I was just a little confused by the term
Right.
bias. It seems like what we talked
Right.
about yesterday, especially when
Right.
Mike was presenting, it seems like program context and client
Right.
characteristics, and this
Right.
is just a program context that leads to heterogeneity of
Right.
treatment effects. And so you're just elucidating sort of, this is a way in which it exists that we're not always cognizant.
Right. I would just, the only thing I would say is let's see how the person who wrote, this is your assignment, by the way, how the person who wrote the study talked about it. Did they talk about it in a way that's subject to bias or not? I think that how you talk about it is going to. I agree that it's a very cool thing that for a subset of people we have in our hands under pretty weak assumptions a real causal effect. We're not quite sure who those people. We may not be quite sure who those people are, and so. We just have to be open to different things. Like, see, I'm in this charter school thing, and I'm a little worried that some of these charter schools are very severe on what you have to do to participate, and they therefore select a certain kind of person who's willing to participate in a very, let's say, aggressive regime. And another charter school doesn't do that, and they say, well, one's more effective than the other because they have a larger local average treatment effect, but they might be working with a very different subpopulation, and therefore, the statement that this one is more effective than this one is potentially a biased statement because you're talking about more effective for different kinds of people, and that statement assumes when A is more than B, you're assuming a commensurable, you're comparing like with like when you say that. That's all I'm saying. Okay. Yeah. So in sum, we can estimate the population average effect of participating if we assume, actually 3 things I didn't put up, constant treatment effect. And the no covariance assumption is sort of a special case of that, because if one of these is a constant, then, well, I guess one of them is no. If the product of those is a constant, then there's no covariance between 2 constants, involved with it. So constant treatment effect, no covariance assumption, or we can estimate this other thing, not the average treatment effect, but the local average treatment effect. And I sort of like the Complier average causal effect a little better than local average. What locality are we talking about? Complier average causal effect I like a little better. It's a little more descriptive for me, that it's the average for the compliers. The compliers are the people who would participate if assigned and who would not participate if not assigned. Oh, I do want to make one sort of another observation. When you have the one-sided compliance, where the only way you can not comply is if you're assigned to the treatment and you don't participate, then we can look inside the experimental group. We can see the people who we can know who the compliers are. And now we're on much stronger ground. And
Compliers are, you're actually
no,
treated. And there when you do this, you're getting treatment on the treated.
Exactly.
Which is different
Right.
than the complier average
Right.
causal effect or late.
Right. And you can say who the treated are.
Subpopulation.
And you can say who the treated are.
Yes.
You can. So if we have one-sided compliance in every site, and we find different effects, we can say who is treated in every site in detail, because we can observe those people. The two-sided compliance is the one that creates the biggest problem. That's when it's more. It's sort of like the non-compliers are a blatant subgroup instead of latent, right? Yeah, one-sided, because you can see them, you know who they are. Okay. So how do we take this? So now we're going to take what's, this machinery, and we're going to replicate it across sites. That's the whole project here, right? And so we're going to estimate the average effect of program participation, and we're going to estimate the variation in the impact of program participation, and we're going to do that a little with some sort of trepidation, because the different subpopulations thus served may be different, and so the variance in the effect could reflect. We have to be careful that it could reflect the variance in these subpopulations. But we're still gonna do this, and maybe we'll find the effect varies hardly at all, and then we don't have to worry as much. And so, and we're going to use 2 methods using simulated data, and the data are simulated to sort of look like, I guess, maybe a beefed-up small schools of choice design, which is a study in New York, right, that had, you have 100 sites or 200? How many? Okay, well, we used 200 when we generated this data set, and each site has about 100 people, so it's a huge study, a huge data set. And so it's a simulated data set, and some of our assumptions, as are met. So, but we wanted to have a big data set we could simulate, try the different methods, see if they got good results, and I think you'll see that they actually do give very good results. Doesn't mean that they're always going to give good results, but it was a good start because this is a new idea. So we're using sort of a hypothetical idea that there's earnings, and we're going to say the average effect of participating in this program, Small Schools of Choice, is 1.194 thousand. So read that as a comma, $1,194 on average annually, and the variance of that effect is 0.430. And we're going to use a couple different methods and see if we can recover that, right, in this big data set, just so you'll see how these methods work. And you'll see that the methods have different assumptions, and you'll see that one of the methods will generalize to when you have multiple mediators. When Sean does his talk, you'll see that one of the methods actually can be generalized to more than one mediator. That's kind of where we're going with this, all right? So the first method is we're just going to do the 2 ITT analyses. We're going to study the intention to treat effect of T, random assignment, on the outcome Y. Then we're going to study using the multi-site methods, exactly the things that we talked about yesterday. We're actually, in this case, going to use the FIRC, the fixed intercept random coefficient model that we talked about yesterday. And then we're going to do the same thing, but now we're going to have the intention to treat effect of T on M. And then if we have those two intention to treat effects, then you'll see that in a multi-site trial we can combine the results to get an estimate of the average treatment effect of participation, or the average of the complier average causal effects and their variance across sites. Okay. So what we did was we estimated. So we used our left centering. This is the earnings outcome centered around the group mean is equal to B sub j times the treatment indicator centered around its mean outcome. B sub j is in site J the model under the model. B sub j is the true causal effect, ITT effect of T on Y in site J. In fact, all it's going to be is in the subpopulation. Well, it's going to be, let's say this right. It's the mean difference between the earnings if everyone in that site was assigned versus the mean difference if no one in that site was assigned. That's what B sub j effectively is, and we can estimate this under randomization very easily by each one of these B's by just taking the sample mean difference between those assigned to the treatment and those assigned to the control. The sample mean difference is going to be the estimate, a least squares estimate, if you will, of the impact of the ITT effect of T on Y. And then we're going to say that's our level 1. We call this an HLM, our level 1 model. Within each site, we have this model. Then looking across sites, the BJs vary around the grand mean beta, and the variance is equal to tau squared B. We did this stuff yesterday. And what we get using the methods of yesterday is we get an average effect of assignment, random assignment, on earnings of 0.770, which is $770. And we get an estimate of the variance of that across sites of 0.249, which is about 0.50 squared, so about $500 standard deviation across sites. That's what we get. Okay. So sometimes we compute, under the possibly questionable assumption that the true effects are normal. We could say, this is kind of a nice little thing to do, is say that if we really think these treatment effects are normal over sites, we could say, well, we think about 95% of the impacts across the population of these sites would be 770 plus 1.96 times the standard deviation. So somewhere between $210 and $1,750 is kind of where so that gauges what we think according to, this is using the method that Howard introduced yesterday. Sort of, the distribution of ITT effects across sites ranges from kind of small negative to some pretty big positive effects. It's under normality, which of course, that's just a kind of a way of roughly characterizing, how much heterogeneity is there? Because we see these variances. What do they mean? This is just trying to say some sites, it could go from here to here, sort of make it more concrete. Okay. Any questions about this? Is kind of more or less just straight from yesterday, ITT effect using the fixed intercept random coefficient model. Okay. So we do that. Then we do exactly the same thing. We just substitute M, which is our participation variable. M is a 1 if you participate. We just use a linear probability model to kind of keep it simple. And we're going to regress the centered M on the centered T. And so now G sub j is the ITT effect of T on M in site J, the average. So the average, and this is kind of what we're calling compliance. G sub j is the compliance rate in site J. And the average of those is gamma, and we estimate that to be 0.703. So that means that on average, being assigned to the treatment increases the probability of participation by 70%. That's the average. And then there's a variance of that, and we have a 95% plausible value interval. And what this says is we think that the true compliance rates across sites, there's a missing decimal point there. I see that now. Man, when these things get big, you can really see the typos. 0.55 to 0.86. So the compliance rates go from 0.55 to 0.86. So that's what the data are telling us. 95% of the sites have compliance rates between those two numbers, right? Okay. Again, use the same methods that we had yesterday. So the sort of and so now that we have these two things, we can actually just compute two things. Just combine the results. Well, we have a delta. To get our delta, we can just divide the beta by the gamma. Yeah. 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 Right. Right.
Do we feel like we measure compliance
Badly. I think we do.
Yeah.
Because if you do another, think about sampling. If we do another random sample that was small from that site and did it again, we'd probably get something different. So if we replicated the study within that site identically, under identical conditions, we'd probably get these things would jump around by chance. So the idea behind this tau squared idea is that we're supposed to be squeezing out all the noise. So we can estimate, in other words, the idea is basically we can estimate how much those estimates vary. And if we have a good theory that tells us about how much sampling error there is, we can kind of back out how much true variability there must be, and it's that. That's actually the way it works. Because as Howard showed that, in fact, if you have small sites, these estimates could have this huge distribution. But we really don't, we think a lot of it's noise, so we really think the distribution is this wide after we squeeze out the noise. Are you with me? Is that clear? Now, one of the problems with small sites, too, is that it's harder to, when you have a lot of noise, it's harder to know how much, it's harder to squeeze it out. Although in this case, it's not that hard because we have like 200 sites with 100 people per site. So when we simulated the data, we have this big data set. So we want to see if this thing works under good conditions. But with very, very small sites, this stuff gets, it's a little problematic sometimes. But in principle, we can squeeze it out because we know what the noise is. Okay? And we could just use a method of moments type of estimator. We can use any of those methods that we talked about yesterday, some of which are use very weak assumptions. This is kind of a weird example because it's a linear probability model, which we usually wouldn't do. In a hierarchical model, we wouldn't. We would usually use some kind of a logit model or something, but it seems to work pretty well. So that's what we have. And so we now can, using the old-fashioned sort of delta equals beta over gamma sort of thing, 770 was the average ITT effect of T on Y. 703 was the average ITT effect of T on M. The ratio of those is our estimate of the delta, which is 1.095, so 1,000. So on average, so what we're really saying is that on average, the treatment made people, being assigned to the treatment made your wages go up by, your earnings go up by $770 a year. But the effect of actually participating for the compliers was $1,095. It was bigger, right? It's bigger because the ITT includes the zero effects of all the people who didn't comply. So the division is always going to be, but gamma is always going to be less than 1. It's always going to pump up. It's going to pump up the estimate, of, we hope appropriately because it's taking into account the fact that a lot of people didn't comply, Howard.
So I just want to
Right.
add on to what you were
Yeah.
saying. When Steve computes that delta, that division, that's one overall average divided by another overall average.
Yeah.
So it's not,
Right.
that part is not as susceptible to the issue, the genuine issue you raised, as other aspects of this.
I think Lindsay helped me. I still sometimes look at like measurement error and sampling error, and then kind of it's not that we're measuring the construct poorly necessarily, but that if we do repeated samples of the same thing in the same identical site, you're going to get different results, and sometimes that's what I'm still trying to make sure that I have clear in my head before we're talking about it.
Now the predicted gamma is that which is predicted by randomization, so we think it's kind of more or less free of measurement error. But there's sampling error. But we're using methods we're using models to squeeze out the sampling error, both for the variance and the mean. Right. So, and of course, you can see that. You can imagine that if the gamma hat is really a small number, like really tiny, then the denominator gets really small. this whole thing becomes very uncertain because if there's any sampling error in the gamma, then little sampling errors create these huge differences in the ratio. But the standard error for, and by the way, you know, most people who do this, when they compute the standard error, they just divide the ITT standard error by gamma. If you wanted to be a little fancier, you could do a delta method. You know, you could actually get something that corrects for the fact that the gammas are uncertain, and get something that might be a little more accurate. But that's what we get. And then here's this little thing this little formula. If you kind of, okay, I should have shown how to, if beta for site J is equal to the compliance times the effect, delta, then the variance of beta is a function of those two things. So how much the ITT effects vary is going to be a function of how much the participation rates vary and how much the effects vary. And then if you kind of just solve for the variance of the site-specific effects, you take the variance of the ITT effects minus the square of the overall, the thing we just computed, times the variance of the participation rates divided by the sum of two things: the square of the participation, the compliance, plus the variance of the compliance, and you can get an estimate of the variance of the ITT effects. Unfortunately, under the assumption that the compliance and the effect don't covary. So to get the variance, we have to go back and make that stronger assumption. I don't see any other way to do it. I've been trying to figure out how you can do it, and I can't seem to do it. So, because otherwise there's another unknown in that equation, and we can't solve for it. There's a covariance that we don't know. We can't estimate. So under that assumption, we do this little plug-in thing. Here was the variance of the ITT effects. Here's the square of the causal effect of participating times the variance of the compliances divided by that, and we get 0.483. And so that 95% plausible value interval. So if we believe that, then we think that in the 200 sites that some of the effects of participation are small negative, and some of them are actually all the way up to $1,248. Yeah.
I think that's a mistake.
You think so? Oh, thank you. I must have screwed that up. Okay. The square root of 0.5 is about 7. Yeah, the square root of 0.5 is about 0.48 is about 0.7. 2 times 7 is 14. Yeah, you're right. That can't be right. You're absolutely right. Sorry about that. Yeah, I got to fix that. Thanks. That was good. Yeah, and I thought it had to. Even the right side of the other plausible value interval is even bigger than that one. So, yeah, no, it's. No, you're absolutely right. This is not right. Maybe I copied that. Did I copy that from the? Yeah, you're right. Look at the right-hand side. Even for the ITT effect, it was bigger. It was 1,750. So obviously, it's got to be a lot bigger for that one. Thank you. Okay. We were kind of happy to see that. Yeah. Oh yeah. Right.
All of these sites. How does that value vary if we could just calculate that each site independently or individually and then average those up?
Okay, so that you can do that, and that's actually a very nice thing to do if every site has a strong compliance. The problem with that works in some studies pretty well. I guess it would work pretty well in welfare to work. Well, welfare to work doesn't have non-compliance, but if you have large sites and a lot of compliance, that's fine. But if some of the sites have very low compliance, which I've seen in a lot of studies, you have this one site or two that have these low compliances, or half dozen, those things blow up. But in our paper with Sean and Takakonomi, we call that option A. Just divide in every single site and then study the variation of those things. Absolutely, that's a good thing to do. Really?
Yes.
Some of those sites are 1 and 1 and 2 and.
If you look at it, the compliance is, for 100 out of 300 sites, compliance is perfect.
But what about a site that only has like 2 kids in it or something?
It never blew up, Steve.
Wow.
Never blew
Okay.
up. I was surprised.
Okay.
Never blew up.
But I will make one. Let me make one statement about this, which is.
They get weighted way down.
Oops, going the wrong way. Hold on a second. I'll get this. I'll get there. One of the nice things about this method is that, by the way, if you use a little weighting on this one, you can be sure that your overall delta is the average among all the compliers in the entire population by weighting by Nj sub gamma j times gamma j. So N is the number of people in a site. N times gamma is the number of compliers in a site. If you weight by N gamma, all the sites, you're weighting up to a complier average population. And you can do this under weaker assumption. You get the same result you would want, exactly the same result, under a weaker assumption. The weaker assumption is here. We have to assume that there's good enough compliance in every site to do what you said. And if we have it, we're golden. I love it. But this one doesn't make such an assumption. The only thing, in fact, this method will work if either one, even if the average compliance is 0, this wouldn't work. It sounds kind of weird, but that doesn't make sense because compliance would have to be negative. But it could be very weak. As long as you have either the average compliance is strong, you get the square of this, or it varies a lot. You can get this ratio. You can estimate this ratio because the denominator can be stable. That's for the variance. Now, but you're right though. For the mean, the average, the key is the average has to be strong. Okay. Yeah.
Another just comment, like if we were just to plot that histogram, would the variance be overstated for the same reasons we talked about yesterday, in that smaller sites would have more sampling error?
No, it shouldn't be. It shouldn't be. You know, it should be squeezing the noise out correctly.
Talking about plotting the point estimates. I think he's talking about plotting.
Oh, plotting the point estimates, yeah. That plot would be smaller than this tau squared, would have smaller variance. If you plot the empirical Bayes estimates, they would be shrunk toward the mean. And a little bit to make them really maximally accurate, you would shrink them a little too far, and then their distribution would understate the variability in the, yeah.
So maybe I misunderstood Joe's question, but Joe's question was saying run the latent every single site and then plot those point estimates. That would be too.
Oh, they would be, yes.
Okay.
That would be, they would have like variation like this, but we could use the empirical Bayes procedure. We call it option A, and using exactly what you said. In our paper, the 2012 paper, that's exactly what we said. And that's kind of a nice option because now we completely avoid the no covariance between compliance and effect assumption. Right, Sean? Yeah, okay, good. Okay, let's see. So I want to show you this one other method, and then we're pretty much wrapping it up, which is, I think, time to do that. We can use something called, we can use a multi-level version of two-stage least squares. You guys are familiar with two-stage least squares. This is a different method. And this, what we do here, but this is going to require a little bit stronger assumption, actually, for the gamma at least. We are going to take, so what we do is our first stage, what we did before, the ITT effect of T on M, and our second stage, and we get the G, and then the second stage, our theoretical model is that Y depends on M, but we don't want to do the regression. Remember we said we don't want to do that regression because it's biased. So what do? We plug in, we get the predicted values of M from stage 1, and we plug them in, and we do our FERC model, if you will, on this, and we plug in M hat from, this is the predicted value of M given the ITT, and we do the regression, and now we recompute. There's a little trick here. Here's here's a little problem in theory that doesn't seem to arise actually in practice, as far as I can see. The problem in theory is that when we estimate this model, we actually don't get the right variance because we're getting the variance as a function of where m hat is the predictor. The true variance should be, as you get the right deltas, should be with m as the predictor. See, we want to go back to our theoretical model, and our variances here, the sigma squared here and the tau squared, assume that we're using m, not m hat, as a predictor. And so we should correct our variances. That this is in, you can look in green or in any of the econometrics books. You're supposed to recompute your variances. And we have a program that does that. It doesn't ever seem to make any difference as far as I can tell. This idea of regressing, oh yeah, just one second. Wait, let me see. I'm going to make sure I get this right. Yeah, let me come back to that picture. So it turns, so does everybody see this point? I think you've all seen how to do this. You do a first stage. You get the predicted m. And instead of using the stage 2, where you regress on m, you regress on m hat. But we're doing it in a hierarchical way so that we can still get the mean of these deltas, and we can get the variance. Okay, we can back those out using this kind of two-stage thing. And I want to make a point that it doesn't take a lot of math to show that this is the same thing as regressing. If you knew your BJs, if you knew that the ITT effect in each site, J, it's just equal to the product of DJ, which is the effect of the compliance in site J. GJ is the compliance rate in site J, the way I have my notation. And we can kind of, we can just sort of factor this out and say, well, it's just really saying that BJ equals delta, which is what we really want to know, which is the average effect of participating. And the predictor variable is GJ, which is your compliance. There's no intercept. And you got this, but you got this weird little error term. Okay? And so really, I can then substitute what I do know, which is B hat, which is my mean difference between the two groups under the ITT in site J, regress it on G hat, and I have this error term. This is just the sampling error, not a problem. But there's this problem here. This error is going to be ignorable only if the expected product of G times this dj minus delta is 0. Well, that's the covariance. So right there, only if this is the covariance between compliance and effect. We assume that covariance is 0. Then we can just do this regression. Just take these beta hats and do the regression. But that's really what this two-stage least squares is assuming. We've gone back to the assumption that the compliance and the effect don't covary. So we made this assumption that we're sort of trying to avoid. But I think Sean's talk is going to take this equation right here, maybe slightly different notation, and expand it to where you have more than one delta and more than one G. Delta is the effect of participation, or you could say the effect of the mediator. G is the effect of the treatment on the mediator. He's just going to take this and expand it. So if you understand this, it should be pretty easy to understand that. And we're still going to have to make this assumption. And what we got is delta hat is 1,095, and the standard error is 0.07. Now I'm beginning to wonder. Yeah. And essentially what we got was, let's see, 0.486 and 0.697. I want to go back to my other results. Oops, wait a minute. Yeah. Well, basically, if you look at the two sets of results, they're almost identical using the two methods. Now, the fact that they're almost identical doesn't mean that they're always going to be almost identical. They're almost identical because in the data set that we actually simulated, we didn't have any covariance between compliance and effect. And that's the key assumption that we had to make is true. So, but we were heartened to realize that at least under those assumptions, using the two methods, we get exactly the same effect result. So, okay, so I think it's time for me to wrap up. We have an assignment somewhere. Do you all have it? For take a break now, right? And I guess you can take a break and reassemble in your groups. And we have this little assignment here. Let me see if I've got more copies. And what we have, anybody need it? Anybody need a copy? What we have, over here, a copy, is, anybody over here? Okay, sure. We have on the back page some real data, some actual results from Howard and Mike's study of the Head Start, National Head Start Impact Study. And we've got some ITT results, and we've got some local average treatment effect results, which are, or you know, effects of program participation type results, which are obtained using a variant, at least of one of these things that I just did. And your task is to answer the questions on the front. A lot of it has to do with telling somebody what these numbers mean in a way that's intelligible, but also true. And then also kind of just taking stock of what are the assumptions might be required. This is just to get used to talking about this stuff. I think this is really, really important, being able to translate these models and these numbers into words. Howard, did you want to say anything about how you estimated these things that would be relevant here?
I don't think it should change anything about the assignment. We actually, you've got option B and
right.
your option B from your paper.
Right. Option B is where we do the division, right? Yeah.
You've got your option C from
Right.
your paper, which is where you run the regression of the ITT on the outcome on compliance. These were actually a different option where we did what Chris was describing, where we estimated site by site the local average treatment effect, and then did a random effects analysis
Right.
It didn't blow up, didn't even come
Right.
close to blowing up.
Right.
And we also did it using your division,
Right.
and the results were very similar.
Right.
So we did it another way, but on real data, not simulated data. So, but they're getting at the same thing.
Right. Yeah, one thing I want to just, in closing, I want to emphasize, it might have been a little confusion at the end, that I just want to make sure that everybody realizes that this two-stage least squares thing, which is the thing you're probably kind of familiar with, where you get the M hats and you plug them in at from first stage and plug them in at the second stage. The assertion is that that is the same as actually just in a level 2 model, a between site model, regressing the estimates from each site on the ITT effect in each site, regress it on the ITT effect on the participation with no intercept. Those things just, if you guys want to, I'd be happy to show you how that works. It's pretty easy to quickly show that doing those two things is the same thing, as long as you have some estimate of the variance of these sampling errors, which we can typically get quite straightforwardly. And I just want to make the point that bridge, that understanding that two-stage least squares is like this regression of ITT effect on outcome being regressed on ITT effect on participation, is what sends us into being able to do it's that insight that enables us to go to where we're going to go this afternoon. All right, so we're going to have a break. We're going to reconvene in our groups. And let's take, 15-minute break, reconvene in our groups. We'll walk around, talk to you guys, try to see if you can put some words around this stuff. And then we might have a little discussion if we have time to see what your answers were and see whether we agree on that. And then we'll have lunch, and then in the afternoon we're going to soup it up, and we're going to have more than one mediator. We're going to go into a generalized mediation analysis. All right?